to summarize Chapter 8, here we go. We started off Chapter 8 with exponential growth and decay functions. This function would begin at 800, and since it's greater than 1, it's increasing. It's growing. Where this one starts at 800, but it's less than 1, so it's decaying. So we first started off with a beginning value, and the value you took to a power. If it was bigger than 1, it was growing. If it was less than 1, it was decaying. Then what we did, after we did the graphs, we then switched over to the interest rate problems, which this is the same as this. This is the same as this. It's just I have different letters. But it's basically the same exact thing. A stands for your final amount. P is 800, your initial amount. Instead of 1.25, I did it as 1 plus 0.25. So my interest rate is 25%. T is number of years. Here this is 0.75, so that would be 1 minus 0.25, which means it's a decay of 25%. So these blue equations are just the same as this, but showing it in the terms of a word problem. Now the next question was, what if we wanted to try to solve a word problem like this? What I said here is, see how this is the same as this, except I have a 10,000 here? The question is basically saying, if I start with 800, I have 25% growth. I want to make 10,000. How long would it take? So to solve that, you first would divide the 800 over, and when you got to this, you kind of got stuck because you have a t as a power. So what happened is you had to develop something called a log, or some other opposite function of exponents. So an undoing of exponents. And what happened is they developed the log. And the way you do that is you simply put the word log in front of this right here. You put the word log in front, and then you switch the t and the 12.5. So the t went over here, the 12.5 came inside the log, and from there they created the way to undo or open up an exponent. And you could find t. The question then is, how do you find this? Well, what happens is you can find these using a table of logs stored in a calculator. And when you divide the log of the top, or the base, this piece, divided by the log of the base, which is right here, you do that with those two values out of your calculator, you get 11.3, which that is how many years it would take to go from 800 to 10,000 at 25% a year. Okay, so they developed a log structure to solve a word problem. Now, this log, then once they got this log thing, they have to then go back and undo logs back to exponents. So you have to be able to go from logs to exponents back and forth. And that's what this box is about. If we focus right here on the transformation, they have an exponent. What they decided is, okay, let's learn what we can do with exponents is we can change them into something called logs. And all we do is we write the word log in front, and we switch the x and the 81. Now it's in a log form. We could then find this log form using tables of these values. Now, they also had to be able to get back to where they started. So in order to get back to where they started, they just said, oh, get rid of the log and switch it back. We're back to where we started. You can go back to the log and you can switch back. Just like they call it transforming, like Transformers or More Than Meets the Eye. You change back and forth between robots and cars. You're changing back and forth. That's the basic building block, and that's what they used to solve this. Okay? Now, there are two basic structures of logs, two major ones. The log we use mostly is just log. So log 8 is really a log base 10 8, and so many people forget that. They forget if there's no base, it's base 10. Second of all, is the most common, ln 5 is log base e5. You ever see ln? It's called natural log, it's base e. So there's two basic logs, okay, and those basic logs, this is base 10, this is base e. Now, from there, they also have one more thing which I didn't write on here, but if we have log, say base 5, and say this is 32, you can rewrite this as log 32 over log 5. There's a property where you can rewrite this as this. And that's how you solve a log. We use that over here, right there. But this property is what we used. So if you have this, you can rewrite it. Now, one more property of logs. There's a couple properties of logs where we expanded and condensed. Okay, when you go from here to here, what you're doing is you're expanding. But when you go from here to here, you are condensing. So what happened is we went from expanding to condensing, and we go back and forth. Just like we went back and forth on transforming it, we have to learn to expand it and condense it back. Because if you do one thing, you have to undo it. So the way we learn the properties of logs, what happens, because basically we use logs, thus we have to then learn how to use the basic premises of a log. So in a log can be expanded by, if values inside the log are multiplied, it's a plus. If values are divided, it's a minus. Those are two properties of logs. The other property is, when you have a power, powers, see x to the fourth can jump in front. Y to the fifth, the power of y to the fifth can jump in front. So that's expanding, and then you just go backwards, you get back to condensing it. And you have to learn to do both back and forth. Math, again, is full of do something and then go back to where you started. So we got exponential growth and decay. You got to solve it. You got transforming. You got some basic logs. You got properties of logs. This is called your change of base formula, which is how you solve them. And then here's another example of just solving a general log. This was solving an exponent. This is solving a log. So for this particular example, if I want to solve this, the first thing, there's a plus. So we use properties of logs to multiply these two, and I get x squared minus 4. Then I use this property, switch it back to an exponent. So I drop the log, switch these two. Okay, remember, these two just got switched when you do that. And you get t to the first equals x squared minus 4. Then you add the 4 over, square root both sides, and you get plus or minus the square root of the square root of 14, which is plus or minus 3.7. Now, I used to tell you that you have to check for extraneous, and you do have to check for extraneous, but the problem is, if I put the positive 3.7 in here and here, we're okay, because those are positive. But if I put negative 3.7 in here, doesn't it malfunction it? But, look at this. What if I plug the negative into this one? Does it still malfunction it? No, because when you square a negative, does it make it a positive? So is the negative extraneous? I don't believe so. Because, yes, it's extraneous when you look at the green equation, but when you plug it into the red equation, it's not. So it actually looks like it's extraneous, but it really isn't, because it could be plugged into the red form of the equation. Kind of weird. Kind of something you got to watch out for extraneous solutions, because an alternate form allows it to actually be a value that works. Okay? So it's both a positive and a negative 3.7 are your values.